Constant pressure calorimetry. Many chemical reactions happen in aqueous solutions, that is, liquid. The apparatus to the left is a calorimeter. We have a styrofoam cup on the outside here. We have a stirrer that pokes through this insulated cover, and we also have a thermometer poking through and measuring the temperature of the water, and the stirrer is used to stir it up if we're trying to get a reaction going. How could you use this to measure the heat change for a chemical reaction in an aqueous solution? And you can see the water, the fluid down there, which makes it aqueous. Think about it for a few seconds, and we'll pull the answer tab out here so you can pause this video. Okay, come on back. The answer is we could carry out a reaction in an aqueous solution in this calorimeter. The heat change can be indirectly determined. The heat change of the solution will have the same magnitude as for the system, but the opposite sign. So the heat change in the surroundings would be 300 joules. The heat change in the system would be negative 300 joules. Now, the answer tab on the previous slide cut right to the answer without telling you how we got there. So now let's fix that and tell you what we did. We know the specific heat for water. It is 4.184 joules per grams Kelvin. We can measure the change in enthalpy for the reaction by measuring the heat change in the surroundings, okay? Here's all your surroundings here, using the following equation. Change in enthalpy is equal to Q, which is mc delta T, and of course we're at constant pressure, right? This lid here, the pressure on it is atmospheric pressure, and that stays the same. Delta T would be T final minus T initial, and for an exothermic reaction, delta T will be positive. For endothermic, it will be negative. So the heat change in the surroundings has the same magnitude as for the system, but the opposite side to that of the system. Here's an example. A student determines the enthalpy change when ammonium chloride dissolves in water, and the way he does it is he measures out 20.00 grams of ammonium chloride and he adds it to 500 grams of water in a styrofoam cup. The initial temperature is 16.1 of the aqueous solution. The temperature decreases to 13.2 degrees Celsius, which is T final. What is the enthalpy change for the dissolution of ammonium chloride? Note, when we use the masses, we're going to add the mass of the water and the ammonium chloride. We have to conserve matter here, of course. So delta H, the enthalpy change of the surroundings, is the total mass. So it's this 500 plus 20, right? The 500 is the water and the 20 is the ammonium chloride. We multiply that by the delta T, and it's a negative delta T. The temperature decreased. Here, C for water, 4.184 joules per gram Celsius. And we get negative 6,300 joules. Heat was lost from the surroundings. The temperature change was T final minus T initial, which is a negative number, which means that heat was lost. Again, from the surroundings. That's who we're talking about here. That's the fluid around the reaction. To finish this up now, we know that we lost heat from the surroundings, and as mentioned on the previous slide, the solution is the surroundings. We needed an equal amount of heat being gained by the system, and the system was the ammonium chloride dissolving. Therefore, the change in enthalpy for dissolving ammonium chloride is a positive 6,300 joules. This is an endothermic reaction, and we mentally kept track of the heat flow to assign the sign with respect to the system at the end. And you can go back a few slides to see the relationship of delta H to endothermic and exothermic.